Welcome to the lesson on image filtering with MATLAB. In this lesson, we will learn how MATLAB can be used to apply the most common types of filtering techniques to images, including linear smoothing and sharpening filters, and nonlinear filters such as edge detection filters, median filters, and matched filters. Similarly to the filtering we did with signals, the problem of linear image filtering can be introduced from a frequency filtering perspective. Recall low-pass signal filters, such as the box and Gaussian filter. These are filters that filter out high-frequency content and let the low frequencies remain. These have the effect of smoothing a signal because sharp transitions between signal values are removed when high frequencies are removed through a weighted average of local signal values. Similarly, with image filtering, we can design low-pass filters. Instead of 1D filters, as were used for 1D signals, for 2D images we need two-dimensional low-pass filters. Shown here is a surface height plot of a 2D Gaussian filter, which has a window size W of 20 by 20. Similarly to the 1D version, this filter is a conventional linear filter, and thus it can be applied to the image using convolution. 2D convolution is similar to the convolution function we saw with one-dimensional signals. But instead of sliding the filter in one dimension, with 2D convolution, our filter is two-dimensional and we slide the filter to locations over the two-dimensional range of the image. We compute a weighted average of all the image pixels that fall within the range of the filter window at each image location to filter the image. This Gaussian filter weights the importance of image samples near the center of the image filter, highest in the weighted average. Then the importance weightings in the weighted average taper off as we move to the edges of the filter window in both directions. This 2D low-pass filter smooths an image because sharp transitions between pixels are removed when high frequencies are removed using this local averaging operation. The result is that this will remove noise, but also degrade edge sharpness in the image. High-pass filters, on the other hand, are those that filter out low-frequency content and detect only the high-frequency content. Such filters can be used to sharpen the image or detect edges, but they are also sensitive to noise. In MATLAB, two-dimensional convolution is implemented as the conv2 function. So similarly to a signal, there are functions designed to take as input an image and analyze or process it. The conv2 function takes as input the image and a 2D filter and outputs the filtered image. Some filters, like median filters, are not linear and thus do not use convolution. However, any type of filtering, even types that are not linear and do not have a dedicated MATLAB function, can be implemented in MATLAB with sufficient coding using for loops. Typically, image filtering is introduced with image smoothing filters, which is precisely where we will start. We saw with signals that Gaussian filters have some ideal properties for signal low-pass filtering. The same is true for image smoothing, where we can use a two-dimensional Gaussian as shown here as a filter. Let's go to MATLAB and see how this works. Let's load in an example image to experiment with. We use imread to load moon.tiff. We can display it in a 1:3 subplot. Set our color map to gray. Give it a title. And set our axes to be tight and equal to ensure a proper aspect ratio. We can see we have a stellar zoomed-in shot of the moon. Next, let's see what happens when we filter our image by convolving it with a two-dimensional Gaussian filter. The main parameter we need to choose is sigma, or the standard deviation of the Gaussian distribution. We'll start with a relatively small value of sigma and progressively increase it. So here we'll start with sigma equal to 3. Then we can define our filter using the fSpecial function. The first argument is the string Gaussian, which lets the function know that we would like to produce a Gaussian filter. The next argument is the filter size. For 1D signals, this would be capital W, the width of the filter window. For 2D signals, we provide the filter width in both dimensions. So here I'll choose a 90 by 90 filter width. The final argument is our sigma. Note that typically we would choose the filter width to be 6 times sigma. I'm choosing a window size much larger than necessary here, so that the filter window is constant for larger values of sigma that we'll see in a few moments. We will go up to sigma equal to 15, for which we need 15 times 6 is equal to 90 for our filter width. Let's display the Gaussian filter using a surface plot. We'll put it in the second slot of a 3x3 subplot grid, leaving our moon.tif to occupy the entire first 3x1 column of the 3x3 grid. Then we use the surf function to display the filter image as a surface plot. Here, the height of the plot in the z direction is defined by the value in the corresponding row column entry in the 90 by 90 grid formed by the input matrix. We can give it a title of Gaussian filter with sigma equal to the current value of our sigma variable. Using the rotation tool, we can inspect the Gaussian function from several angles. We can see with a sigma equal to 3, we get a relatively tight Gaussian distribution. Next, let's use it to filter our image. We use the conv2 function with our image and filter as inputs. The third argument we use to specify same so that the output matrix has the same size as the input image matrix. We'll display the result in the third slot of our 3x3 plot grid using the image function. Give it the title filtered image, and we use the axis tight and equal command to ensure the correct aspect ratio without extra white space. The filter has smoothed the image, but the smoothing is somewhat mild and subtle and difficult to appreciate without zooming in on some of the fine details. So let's see what happens when we increase sigma. Next, we'll try sigma is equal to 9. Our filter can be computed using the same call to fSpecial. And we can display it in the fifth slot of our 3x3 grid of subplots using the surf function. And we can see our Gaussian with sigma is equal to 9 is wider and more spread out than the sigma is equal to 3 Gaussian. This means a broader range of image pixels will receive weight in the weighted average computed by the convolution, which should result in a greater degree of smoothing. We compute the filtered image the same way using the conv2 function. We can display it in the 6th slot of our 3x3 grid using the same code as before. Here, the smoothing is not nearly as subtle. We can see a significant blurring effect on the original image when we use the larger sigma Gaussian. Let's try one more with sigma equal to 15. We repeat the same code to compute the filter and display it in the 8th subplot slot. We can see we get an even wider filter with sigma equal to 15. Then again repeat the same code to apply the filter and display the results in the 9th subplot. And now we have really lost all of the fine details of shadows around craters. Most of us can probably see more moon detail with our naked eye on a clear night than is available in this highly smoothed image. The value of sigma roughly corresponds to the radius of pixels that are weighted highly in our convolution weighted average. So with a sigma of 3, a radius of 3 pixels for filtering is relatively local, so many smaller details can be preserved. When we go to a sigma of 15, several hundreds of pixels have a high weight in our weighted average, so all of the fine details get blurred away. The sigma we choose for filtering our image should be chosen based on the scale and magnitude of the noise that we wish to smooth away. For noise that is independent across pixels, such as static type white noise, often very small values of sigma work well. For example, let's consider our moon.tiff redisplayed in the 1st slot of a 1x3 subplot. We can add synthetic white noise to the image, first initializing our random number generator, then defining a noisy image as the sum of the image converted to a double data type with white noise with standard deviation of 20. We display the noisy image in a 2nd subplot. Give it a title. And correct the aspect ratio. We can see that our image is corrupted by random white noise, giving the image a staticky, grainy appearance. If we want to try to remove the noise while preserving most features of the original image, we can try filtering it with a small sigma Gaussian filter. Here we're going to define a filter with a sigma of 1.5. With a sigma of 1.5, our W should be 6 times 1.5, which is 9. So we'll have a window size of 9 by 9. We can define our filter to be a 9 by 9 Gaussian filter with sigma equal to 1.5. And we can apply our filter to our image using the conv2 function, and plot the result in a third subplot. We give it a title, filter to image, sigma equal to the value of, or the floating point value of our sigma printed to a string using the sprintf function. We use axis tight and equal to correct the aspect ratio. Viewing the result, we can see that this relatively mild filtering has drastically reduced the white noise artifacts. Our image is certainly not as good as the original. However, many of the small-scale structures have been preserved and survived the noise reduction filtering. Gaussian filters are the most common low-pass filter for noise reduction. What other types of filters are there? There are a number of linear filter options for high-pass filtering. A high-pass filter aims to detect sharp transitions. These typically correspond to strong edges that are often object boundaries in the image. High-pass filters are useful for sharpening images, as we will see in a few moments. They are also useful for edge detection for object segmentation in images, as we will see in the next lesson. One common high-pass filter is called the Sobel filter. A Sobel filter can be easily created in MATLAB using the fSpecial function with the string Sobel as the argument. This returns what we call the horizontal Sobel filter. As we can see, it is simply a matrix with the first row defined as 1, 2, 1, the middle row all zeros, and the last row negative 1, negative 2, negative 1. So what will this filter do when convolved with the image? At every pixel site, a weighted sum is computed where positive weights are assigned to the 3 pixels on the row above the pixel site, and negative weights are assigned to the 3 pixels on the row below the pixel site. So this filter is computing an intensity difference, akin to a derivative, in the row's direction. We take the difference between the intensities in the pixels in the row above the target pixel with the intensities in the pixels below the target pixel. Slightly higher weight on the central column gives the central column slightly more weight in the finite difference. So what will this do? Well, if we're in a homogeneous region, say somewhere in the black part of the image, or a flat gray region on the moon, the intensity difference between the rows will be close to 0 because the intensities within the filter window are constant. Also, if we're at a vertical edge, like the left edge of the moon, we expect similar intensities in the rows above and below our target pixel, also resulting in values close to 0. However, if we are at a horizontal edge, for example, the bottom edge of the moon, the weighted sum will be a very positive number. This is because we are summing a positive weighted sum on the intensities in pixels above the target, which will be the bright moon pixels, with negative weighted sum on intensities below the target, which are dark outer space pixels. The overall weighted sum will thus be a positive number. Thus, the Sobel filter provides a way to detect this type of horizontal edge as opposed to homogeneous or vertical edge content in an image. What happens on the opposite type of horizontal edge, going from dark to bright instead of bright to dark? For example, at the top edge of the moon. In this case, we positively weight the dark outer space pixels and negatively weight the bright moon pixels. So we expect the Sobel filter to produce a very negative number. This may seem like a problem at first, but actually it can be an advantage. It gives us the ability to detect two different types of horizontal edges. Bright to dark ones will be associated with positive Sobel filter response, and dark to bright ones will be associated with negative Sobel filter response. Whereas non-horizontal edges will have a response close to zero. If we don't care whether it's bright to dark or dark to bright, we can compute the magnitude of the Sobel filter response, resulting in a high number for either type of horizontal edge and a low number otherwise. How about if we wanted to detect vertical edges? Well, let's try transposing our horizontal Sobel filter matrix and see what that looks like. So we've defined our vertical Sobel filter as the horizontal filter transposed. Now we have a filter that positively weights pixels to the left of the target and negatively weights those to the right of the target. For the same reasons described moments ago for the horizontal edges, we expect this filter to have high positive response for bright to dark vertical edges and high negative response for dark to bright vertical edges, and close to zero response for homogeneous regions or horizontal edges. Because Sobel filters can help localize edges, they belong to the class of so-called edge detection filters. Okay, let's try them out. Switching to a 2x3 grid, we again display our original image. And below it, we're going to display a zoomed in region of the image by using the axis function to limit our field of view to pixels 130 to 250 on the x-axis and 360 to 480 on the y-axis. This corresponds to the lower left portion of the moon. Next, we compute our horizontal Sobel filter response, again using the conv2 function. And we can display that result in the second slot of our 2x3 grid. We'll take the absolute value of the result and display it so that we get a high magnitude for both bright to dark and dark to bright horizontal edges. We can give it a title of horizontal Sobel, correct our aspect ratio using axis tighten equal, and next we'll display in a lower subplot the same image but zoom in on the same region of interest. And we can go ahead and do the same thing for our vertical Sobel filter response. Which we can display in the third slot of our subplots. and again display a zoomed in version just below it in the 6th slot. Here, I have intentionally used the image function rather than the image sc function because our intention is to visually compare two filtered images. When our goal is to compare brightness of different regions between two images, it's better to avoid using image sc to rescale the image, as it might make different brightness adjustments with the two images. Looking at the results for the horizontal filter, here we can see a strong response with very bright pixels at the top and bottom edges of the moon. The signal drops to 0 where the edge is vertical. We also see a strong response at horizontal edges of craters. Similarly, for the vertical filter, we see a strong response on the vertically oriented edges. Another type of filter that is commonly used for high-pass filtering, edge detection, and image sharpening is called the Laplacian of Gaussian filter. It's not critical to understand mathematically what this filter does in order to use it, but for those who are interested, here's a very brief description. The Laplacian operator computes what is called the divergence of the gradient of the image intensities. Gradients can be computed using, for example, Sobel filters. The derivative in the rose direction from a horizontal Sobel filter, along with the derivative in the columns direction from a vertical Sobel filter, form a two-dimensional gradient. At every pixel, we thus describe a gradient vector for that pixel with two numbers, the rose intensity derivative and the columns intensity derivative. We can display these gradient vectors using the quiver function. For example, let's go to our zoomed in image. We do a hold on, and we call our quiver function with the vertical component as the first argument and the horizontal component of the gradient as the second argument. We make the lines a little thicker than the default to make them easier to see. It looks messy zoomed out, but zooming in, for example, on the strong edge of the moon, we can see quiver has displayed a small vector at every pixel. Longer vectors indicate larger magnitude of the gradient vectors. So we can see at this diagonal edge of the moon, we've detected large gradients at this point, whereas in homogeneous regions, the magnitude of the gradient is small. The Laplacian computes the so-called divergence of the gradient. This is the sum of the derivatives of the gradient in each direction, which captures the characteristics of the second-order derivative of the image. Divergence captures how much the local vector field is changing. If we're here at row 460, column 139, we see a positive divergence, as the larger vectors for the pixel surrounding it tend to be diverging away from this pixel. But when looking at row 457, column 142, the vectors are converging towards this pixel, which is a negative divergence. Somewhere between these two locations, the vector field is neither convergent nor divergent, which is a divergence of 0. That location, the so-called zero crossings of the Laplacian, is right where the edge is strongest. So this is a way to detect edges. So that explains the Laplacian part of the Laplacian of Gaussian. What about the Gaussian part? This is a bit of a mathematical trick. We typically like to combine low-pass filtering, such as Gaussian filtering, to reduce noise prior to edge detection, since the edge detection process will be sensitive to noise as it is inherently looking for sharp transitions. And it turns out that due to fun math tricks, convolving the derivative, or second derivative, or in general nth order derivative, of a signal with a Gaussian is exactly the same as convolving the signal itself with the same order derivative of a Gaussian. So, instead of needing to compute the Laplacian of the image, we do it to the Gaussian filter, giving us the Laplacian of Gaussian filter that, when we convolve it with the image, both reduces noise and computes the Laplacian. It sounds complicated, but in practice it is very simple. We use f special with log as the argument, which stands for Laplacian of Gaussian. We convolve it with the image using the conv2 function. Identically to how we performed Gaussian filtering. And we can inspect the results. In the second slot of our 2x3 grid of subplots. Since there are going to be positive and negative values in the result, when we use image SC to rescale the image, 0 shows up as gray. You can give it a title. And provide a color bar so that we know what values each grayscale level is mapping to, and use the axis tight and equal command to fix the aspect ratio. Below it, we'll display a zoomed in version in our region of interest. When filtering an image pixel where there is a strong edge with a Laplacian of Gaussian filter, we can see there is a positive band of pixels on the dark side of the edge and a negative band of pixels on the bright side of the edge. Let's reset our zoomed in version of the original image for better comparison. So we can see that the zero crossing between the positive and negative bands represents the lower edge of the moon in our image. This type of filter is also commonly used for image sharpening. To sharpen the image using this filter, we subtract some scalar multiple of the result from the image. Since the filter result is positive on the dark side of an edge and negative on the bright side of an edge, adding a negative fraction of the filter will make the dark side of the edges darker and the bright side of the edges brighter, thus sharpening them. Here we define image sharp as being equal to a typecast double version of the image minus 1 times our image Laplacian of Gaussian result. We display it in the right column of our subplots. with our zoomed in version below it. We can see the detailed craters pop out with greater contrast. Especially on the zoomed in version, we can appreciate how the brighter parts of the edges are made brighter and the darker parts are made darker, using this method to sharpen the edge contrast. We can also see we have simultaneously enhanced some of the image noise. Noise in some of the darker regions, like in the shadow of the moon, that was not visible before, now is quite visible. Sharpening is always a balance between improving edge quality while avoiding too much noise amplification. Not all filtering methods need to be convolution-based. If we come up with some other manipulation we want to try, we can code it. One example would be what's called a median filter. We determine a new value for each pixel intensity to be the median of the surrounding values. We start by initializing our median filtered output image med, as a new copy of our image. Then, to perform a 3x3 region median filter, we use for loops for I running from 2 to the number of rows in the image minus 1, and j running from 2 to the number of columns in the image minus 1. We can then find a value for our median filtered image at pixel ij to be the median of the 9 values in the 3x3 grid of pixels in image, running from I minus 1 to I plus 1, and columns j minus 1 to j plus 1. The all second argument to median tells the median function to consider all the values in the matrix, rather than computing the median of each column of the matrix separately. In this implementation, we ignore the border pixels and simply copy their values to our new image. This is the lazy but computationally faster approach. If we cared about filtering the border pixels, we could easily also include if statements needed to handle the pixels on the first or last row and column. Next, let's display the result. We can use the second subplot to display our median filtered image. Give it a title. And correct the aspect ratio. And plot the zoomed in version below it. We can see that with this nonlinear filter, we get good noise suppression without losing too much fine detail in the image. A completely different kind of filtering is called matching. With matching, we aim to locate a certain pattern or object of interest in an image. Our filter in this case is not a low-pass or high-pass filter, but rather it is a template for the pattern or object of interest. We call this our matching filter. The filtering process is then to compare this matching filter to the region around each pixel in the image and compute a matching score, which is used to determine how good of a match we have between the filter and that region of the image. Let's, for example, load in a new image called text.png. This is an image that contains text embedded within it. We'll display it in the first of a 2x2 grid of subplots. Let's zoom in on the region from rows 33 to 45 and 88 to 99 and put this in a variable called match. We can display it in our second subplot. And we can see that we have found the region of the image containing the letter A. This is going to serve as our matching filter. We also want to add a little random noise to our image so that we don't have a perfect match between our filter and the image. So we reinitialize our random number generator. And we can add white noise with standard deviation 0.05 to our image. Okay, let's say we want to locate every letter A in this image. Well, we have our matching filter already. It's ready to go in our match variable. It provides the template for the letter A that we wish to locate. But how do we compare the image to our filter? The most common way to do this with general grayscale images is to use the Pearson's correlation coefficient function that we used in lesson 2. We compute the correlation between the matching filter and the set of pixels around the target pixel after concatenating both into vectors. A high correlation, close to 1, would indicate that the image has a very similar appearance to our matching filter. Zero correlation would indicate unrelated appearance. Negative correlation would indicate the matching filter has a negative relationship with the result, which could be of interest for some applications. Here, a correlation of -1 would be found, for instance, if there were a black A on a white background in the image. We simply need to slide our filter across the rows and columns of the image and compute the correlation between the filter and the local overlapping image region. First, we initialize our resulting image as image match to be zeros. Then we define R and C to be the number of rows and columns of our matching filter. We define dr and dc to be the integer floor of the number of rows and columns divided by 2. Next, we can use 2 for loops to loop over the image, just as we did with the median filter. To ensure our matching filter always overlaps with the image, we run our rows variable I from 1 to the size of the image in the rows direction minus R plus 1. That leaves out R minus 1 rows to account for overlap with the filter. Same for the column loop. We run J from 1 to the number of columns in the image minus C plus 1, leaving C minus 1 columns out of the loop so that our filter box always completely overlaps with our image. We set our image match value at location I plus dr, j plus dc to be equal to the correlation between the match filter concatenated into a vector and the local image box running from I to I plus R minus 1 and J to J plus C minus 1. So this is the local image box that is the same size as match. And we need to convert this into a vector. So we use the reshape function. To reshape it into an R times C by 1 vector. If we didn't convert these to vectors and we just used matrices, the correlation function would compute row-wise correlations. So we need to convert our two images to our image matrices to vectors. For match, we do this simply using the colon operator. For the image matrix, we need to reshape it into an R times C by 1 vector. Finally, we're adding dr and dc to our I and j indices into our image match matrix. This will store the correlation result for this rectangle in the pixel that lies in the center of the rectangle. Which is better? Location ij is the top left corner of the rectangle, so it would work, but using the center of the rectangle will lead to more visually intuitive results when we display the image. We end our for loops to execute. And we can display our results in a third subplot. And we can see an interesting looking result. We see a mostly gray image with some patterns where the letters are located. There are a few pixels that are brighter than others. Let's find the brightest pixels and draw a box around those locations in the original image. Correlation ranges from -1 to 1, so this is the range of our matching filter image result. So let's see how many pixels that we can find in our image match result that have a correlation score greater than 0.6. Using the find function with two outputs, we get the row and column indices to those locations in the image matrix. We can see that box C and box R are 10 by 1 vectors. That means that only 10 pixels in the entire image have a correlation with the filter greater than 0.6. Next, let's create a display function that will draw a box on our original image at the location of each of the high score matching filter result locations. We'll call the function draw boxes with the input arguments box R and box C, which are the row and column locations where we want a box. There will be an optional third input, col, for the color of the drawn boxes. If the number of arguments n is less than 3, we default col to be the character R for red. The first thing we do is define the relative positions for the vertices for the box that will be shown centered at each input coordinate. We can define relative box coordinates for a box centered at row and column coordinates 0, 0. We'll call these box C and box R for our row and column coordinates. So we'll start with column and row position -1, -1. And this vertex is going to be connected with a line to the right to column 1, row minus 1, connected with a line down to row 1, column 1, connected with a line to the left to column minus 1, row 1, connected back to the original vertex at minus 1, minus 1. So this lets us define a 2 by 2 square centered at coordinate 0, 0. If we multiply both of these vectors by 7, we now have a 14 by 14 pixel square centered at coordinate 0, 0. We can take this base square and translate it to lie anywhere in the image. If we want the square to be centered at row 6, column 10, we simply add 6 to our row vertices and 10 to our column vertices. This would translate our entire square to be centered at row 6, column 10. We know where we want our boxes to go. That's in our input vectors, box R and box C. So we can go ahead and plot all of our boxes. We loop over the length of our coordinate vector. This is the number of boxes that we want to draw. And we plot our column vertices translated by our box center column coordinate in box CI. And our row vertices translated by our box center coordinate for the row in box RI. And we'll plot that with color col. And that's it. Let's go back to our original image plot. And we call our draw boxes function with our 10 brightest pixel coordinates in our matching filter result as input. With this visualization method, drawing boxes on the original image is much easier to understand the matching filter result than just looking at the matching filter output. We can see that we have indeed localized our A's, but we've also localized the letter E. Upon inspection, I think that it's fairly clear that our matching filter for the letter A has quite a bit of overlap in shape with the letter E. We would expect our matching filter produces a higher matching score for A's than E's. So perhaps our matching threshold of 0.6 was not quite strong enough. Let's try 0.75 instead. We can see that this gives us a total of 3 pixels in our matching result. So let's redraw our image and use our draw boxes function again. There. We can see that now we have indeed localized the three A's in the top text of our image using our matching filter. But there are also A's in the vertical text on the right side of the image. These were not localized. Why? Well, our matching filter is sensitive to orientation. Our filter is a normally oriented A, but these A's are sideways oriented. If we want to localize a rotation variant structure using matched filters, we need to rotate our matching filters to the different orientations that we would like to detect. So let's reorient our filter. With how these A's are oriented in our image, if we transpose our match filter and flip it in the up-down direction, then our filter will match the orientation of these sideways A's. Then we can apply it to our image identically to before. We initialize our match filter result. We redefine our R and C variables based off of our new filter, and same for dr and dc. Then we use for loops to slide our filter across the image only this time the result is going into image match 2 and our matching filter is in match 2. We can then display the result using our draw boxes function. And we'll display them as green boxes. And we can see after reorienting our matching filter, we now detect the sideways A's. Matching filters don't apply to only text and images. Anytime there is a pattern or structure we want to analyze, matching can be used.